During this presentation, I may use some acronyms that you haven't heard before, but I think they will become more familiar to you as we discuss deep sleep and its advantages. RTCC stands for Real-Time Clock Calendar. This one you probably know. It is a microcontroller peripheral for keeping time and triggering alarms. The DSWDT, or Deep Sleep Watchdog Timer, is a new wake-up source for deep sleep applications. ULPWU means ultra-low power wake-up. That is a time delay wake-up source that does not require an oscillator. The DSBOR, or Deep Sleep Brownout Reset, is a low-power voltage monitor that prevents the microcontroller from executing if power drops too low for safe operation. On prior PIC microcontrollers, sleep mode was provided to allow low power use by shutting down the processor core. However, SRAM remained powered to retain data. To completely stop power consumption, an external switch circuit will be required to cut power to the microcontroller. On new PIC microcontrollers with deep sleep capability, both the processor core and SRAM are powered off to drop power consumption to virtually zero, eliminating the need for an external switch. Certain key peripherals can be configured to remain powered on, allowing greater flexibility for applications. Microchip parts do not need a separate VBAT pin for powering the RTCC. Instead, power is provided through the normal VDD pin, so adding a second battery for powering the RTCC is not necessary. Fewer pins are used, and power levels are so low that applications will not need to add an external switch to cut power to the microcontroller when only timekeeping functionality needs to be powered. Deep sleep reduces current to minimum levels by turning off power to most of the chip's SRAM, cutting current consumption to 90% less than traditional sleep mode. While SRAM does not retain its data when powered down, there are two general-purpose deep sleep registers that will remain powered, allowing some context data to be retained easily. If more data needs to be saved, self-programmed flash, or EEPROM memory, if available, is also an option. On parts with an internal core voltage regulator, the regulator is shut down during deep sleep to conserve power. The voltage regulator needs time to stabilize before the part can wake up from deep sleep. Therefore, deep sleep can typically take 1 to 2 milliseconds to exit on these parts. On devices that do not have a core voltage regulator, wake-up times will be faster, typically 50 microseconds. Waking up from deep sleep causes a power-on reset, so execution will resume at the reset vector, rather than at the instructions that follow the sleep instruction. Special function registers will reset to their power-on reset default values. However, certain registers, such as tris bits, will not affect device behavior until the deep sleep release bit is cleared later by software. We'll talk more about the release feature later during the firmware overview. Deep sleep is great for applications that are inactive for long periods of time, such as remote controls, input devices, sensors, and thermometers. It is also ideal for applications that need to keep accurate time while consuming minimum power. Deep sleep supports continuous operation of the real-time clock calendar where desired. So, what is the big advantage that deep sleep provides for these applications? The longer an application can stay in deep sleep mode, the lower the average current consumption of your device will be. Normal sleep mode is still recommended for applications that need ultra-fast wake-up times, complete state retention, or will only be inactive for short periods of time. Now that I've introduced what deep sleep is, let's take a closer look at how an application can lower average current consumption by implementing deep sleep. This graph shows a typical low-power application actively running at 4 MHz with a current consumption of 1.5 milliamps. Not bad, but still enough power consumption to drain a battery within a month or two. Say that the application no longer needs to be active. The application can execute a sleep or power save instruction with deep sleep enabled to power down and conserve power. While in deep sleep, the device is at its lowest power state. With minimal features running, power consumption can be as low as 20 nanoamps. Certain features, such as the real-time clock calendar, deep sleep watchdog timer, and deep sleep brownout reset, can be configured to remain active if desired. Maximizing the amount of time spent at deep sleep current levels will lower power consumption the most. At deep sleep current levels, a battery can provide power for years without being depleted. Eventually, the application wakes up. On devices without an internal core voltage regulator, wake-up times can be as low as 50 microseconds. Other devices may require 1 to 2 milliseconds for deep sleep wake-up due to core voltage regulator losses. Finally, the application resumes active operation, consuming the most power. The progression through each of these states over time defines the average power consumption of the device. While running, the average current drawn by the application would be the full run current of 1.5 milliamps. By maximizing time in deep sleep mode during periods of inactivity, the application can dramatically lower average current.